Welcome to the AMATIC 2014 webinar series, another look at the challenges of teaching and learning infinite series in calculus with Bob Cappetta, and this presentation is sponsored by the Mathematics Intensive College Mathematics Committee of AMATIC. And AMATIC is the American Mathematical Association of two-year colleges, and our core value is building expertise and exhibiting leadership in the teaching and learning of mathematics, enhancing personal growth, and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. And for more information, please visit our website at amatic.org. And please note that the views expressed by the presenter are not necessarily the views of AMATIC, and any commercial products mentioned by presenters are not endorsed by AMATIC. And now we're going to switch to the presenter slides. So without further ado, I'm going to turn this over to Bob. So if you could welcome him in the chat room, that would be great.
Thanks so much, John. It's great to be here with you folks today. I'm thrilled that we have close to 30 people on a early Friday afternoon, late Friday morning to discuss teaching and learning calculus. I think it shows just how serious and committed those of us are who teach at community colleges. So I certainly hope that you enjoy the presentation. I would like it to be interactive. I will do my best to follow the chat if questions come up during the discussion, and I will be happy to stay as long as I need to address and answer some questions at the end. My name is Bob Cappetta. I am at the College of DuPage, which is in western suburban Chicago. We're about 15 miles directly west of the city. I have been here for 20 years, teaching for 25. And for the last few years, my research interests have been focused on how students learn calculus, and in particular, infinite series. And before I get started, I want to thank Paul McCombs from Rock Valley College, because a few years ago, he was beginning his work on his dissertation, and he and I discussed infinite series, and we did some early research, and he was able to recently complete his studies, and I certainly thank him for inspiring me and for sharing his recent literature reviews. So if this webinar gets boring today, work on that question that's on the screen. So find all positive values of B for which the following series converges. I believe this is a question that I borrowed from Stewart's calculus. It's one of my favorites. It's a non-trivial question, and it's one that certainly causes some challenges for some students. So yeah, when it gets a little boring, you can sit down and work on that problem, and we'll talk about it at the end of the presentation. So here's our first poll question. Do you agree with the statement or not? Yes or no? Each real number has a unique decimal representation. So I will let you go ahead and vote. We'll let John collect those votes, and we'll see what people have to say. Okay. So I'd say that's pretty good, John. Why don't we go ahead and end the poll now? So looking at that, we had 10 people that said each real number has unique decimal representation, and we had 7 people that said no. And that's almost a sign of a good question when you have an opportunity to discuss those things. So hopefully after we look at some of the slides, you'll see what I believe the answer to that question is. And here we go. Here is our first look at that. 0.999 repeating is less than 1 is a statement that many students believe. And there's quite a bit of research on this question. And I would encourage you to ask your students in Cal 2 whether or not they agree with this. So do they think this is a true statement, or do they think this is a false statement? Here's a nice little cartoon talking about Zeno's paradox. Because frankly, the 0.99 repeating question is in essence a notion of Zeno's paradox. What does it mean to go to infinity? What does it mean to move? The engineer will get there. The mathematician doesn't think he will get there. Here are some student responses to that 0.99 question. One student says it repeats forever, it does not have a definite end, and it cannot be compared to an integer. Another student says it's essentially true. It would always be less than 1, but due to such small differences, mathematicians just round it off. And another student says it's true that it is infinitely close to 1, but it is not truly 1. So you recognize this is a pretty challenging question in terms of what it means. Many of the Zeno's paradox issues are coming up again for us here. Here is an answer that one student gave me, saying 1/3 is 0.3 repeating. So 1/3 plus 1/3 plus 1/3 is 1. So 0.3 repeating plus 0.3 repeating plus 0.3 repeating also is 1. Hence, 0.9 repeating is 1. Interesting how this person used algebra to get there. This is something to think about. You can ask students about the 0.99 question, and many students will say 0.99 repeating is less than 1. However, if you give them the infinite geometric series, they will say that it equals 1. So why does that happen? This should cause some cognitive conflict. But if the student sees the geometric series question as just an exercise, run the numbers through the formulas and get an answer without reflecting on what it means, then the student may maintain that incorrect solution. Alcock mentions this as well. If students have an internal sense of authority, they link their visual and symbolic representations. So if they feel they are responsible for their own learning, they do their best to coordinate these multiple representations. But students with an external sense of authority believe that written work is a set of conventions and procedures. So the question I'm going to have for you folks is, as teachers, what can we do to help students develop that internal sense of authority? What can we do to get away from the notion that the student's job is to mimic what the instructor does, but rather create understanding, make sure it's meaningful, so that eventually that student can have that internal locus of control? So continuing with the Zeno's paradox discussion, this is a standard approach that we might use in a pre-calculus course, and maybe even use in a Calc 2 course to look at the behavior. So I'm sure most of us have seen this before. And then the question I have for you is this helpful or is this detrimental? So do you agree that this is helpful? We'll quickly take a vote and see what people say. All right, John, let's go ahead and end the poll. So 17 of 19 people think that this is helpful. And I agree that it can be helpful in that it helps students get a sense for what these things mean. However, I think it also requires us to be careful, because I want to take a look at the next example, which I argue is a variation of this example. If we say 1 plus 2 plus 4 plus 8 plus 16 is L, if we double everything, 2 plus 4 plus 8 plus 16 is 2L. And then if we subtract the first line from the second line, we wind up getting -1 is L, which is infinity. Now, why does something like this happen? The techniques we've looked at so far have been somewhat informal. And frankly, I think that's beneficial. I think it's good to do informal techniques. But at some point, we need to cycle back and say that some kind of a notion like our error terms shrink to 0. So that what may work in one model doesn't work in another. Where this one falls apart is in the first line. We are assuming that that geometric series converges by saying it equals L. With that crazy assumption, we get the assumption that L is -1 or infinity is -1. A little bit of research here, and Tarosha's discussion of potential infinity to me is an interesting idea. So a mathematical process can be carried out for as long as required to approach a desired objective. So it goes on forever and ever and ever. But actual infinity requires you to think about the entire process. So you've got to look at all natural numbers as one concept and thinking about what's going to happen if we hit all natural numbers and then goes to infinity. So if you think of a process that goes on forever versus conceptualizing all of those numbers, you do have a different answer to these sorts of questions. So let me ask you this question. So we're continuing our discussion. Might an expert, so someone who teaches this or someone who understands mathematics, conclude that the sum as I goes from 1 to n of a sub n converges when that sequence goes to 0? So let's see. Do you think an expert might say that? So I'll ask you to respond to that one, and we'll see what we get. All right, John, that's pretty good. So you'll notice that we have a debate, and maybe it depends on our definition of expert. So is an expert someone who is an analyst? Is an expert someone who teaches Calc 2 at a university? Is an expert a high school AP calculus teacher? Is an expert a mathematics major? So maybe it depends on our definition of expert. But you'll be surprised that indeed we have some research that shows that that may happen. So Martin in 2009 gave questionnaires to experts, and they were asked about Taylor series and how students perceived what Taylor series represented. And sure enough, 4 of the 16 experts concluded that the series converges when the sequence converges to 0. So how Martin defined experts, 4 of the 16 made that very, very common mistake that I refer to as the nth term convergence theorem, that of course doesn't exist.
Bob,
So
can we
35% of the people in the study said that. I'm sorry.
Oh, Bob, can we go back to the last slide? I think there was a question about whether or not you meant a sub I.
Oh, I'm sorry, that's a typo. My mistake. It certainly should have been sub I. I appreciate the correction there. So that was not my intention on the slide. My intention was whether or not the experts would use the nth term convergence test. So I thank you for the correction. All right. So indeed, the issue is, though, that the experts had the same concern that the students had regarding the nth term convergence test. Okay, here's a question I'd like you to really think about. So yes or no, do you think students understand the sequence of partial sums definition of series? Okay, thanks, John. Again, 2 to 1 people are saying no. So some people think they do understand, about a third of the people that responded. 2/3 said they don't. So I want to take a look at the research there to see what that tells us about this issue. Martinez-Planell in 2012 showed that the formal definition of a series as a sequence of partial sums does not replace in most students' minds the notion of an infinite sum. Lindemann asks, what does it mean for a series to converge? And I think we might be able to predict what students said. He found that students say it adds to a number or a sum, or it reaches a number. Some might use graphs or talking about infinity. However, he found that nobody made a mention to a sequence of partial sums. I have tried to do that as well, and I have found the same thing. Even though I certainly make an effort to talk about partial sums, I have not seen students that idea stick. So for whatever reason, that is not something that students conceptualize. So we're going to need to address that in our discussion today. So again, do you think students understand the partial sum definition of series conversion? I would argue that the evidence is pretty clear that they do not demonstrate that when asked. Next question I'd like to ask, John, if you could post this one. Do students need to understand the epsilon n definition of convergence of a sequence? Wow, very interesting. 6 people saying yes, they need to know the epsilon n definition, and 14 saying no. Let's see what the research says about this issue. Tall claims that formal definitions are less appropriate for cognitive routes for curriculum development. He says that their subtlety and generality are too great for the growing mind to accommodate all at once without a high risk of conflict caused by inadvertent regularities in the particular experiences encountered. Now, I do not want to dismiss those that said they need to know that. To understand what a limit is, to understand what a limit means in the modern world requires us to understand these epsilon definitions, epsilon delta, epsilon n definitions. In analysis, of course, that is absolutely crucial. The question is, what is appropriate in Calc 2 for the lion's share of students? What do we want students to know? What do we think we might be able to do a little bit later? And I argue it may be beneficial to introduce this on an intuitive level first, have students generate their personal notions of limits as they're creating those concepts. And then once that's established, once they understand how limits work, then I certainly think it is absolutely appropriate to go back to the formal definitions, epsilon n, epsilon delta definitions. Okay, another yes or no question. Do you believe that textbooks include sufficient graphical and numerical representations of convergent and divergent series? So I'm sure we're all using different ones. So John, do you have a question for us for that one? John, it says the poll is closed. Oh, there we go. Let's see what people say here. And we're getting about 4 to 1 people saying no. But there were 4 people that believe the textbooks are doing a decent job with this. And I think it's fair to say some textbooks maybe are doing that. But I believe the research will support those that say in general, textbooks aren't where they need to be. So this is what Gonzalez, Martinardi, and Visa said. Of 17 books they examined, the student was never explicitly asked to produce a visual image of a series or to convert from one register, that is graphical, numerical, to another. So even if the textbooks include this, even if you were the 4 people that said it was there, do you ask students to do this? And I have a feeling all of us, when we're teaching the sum of 1 over n or the sum of 1 over n squared, use a visual, whether it's drawing a graph of that sum and relating it to the integral, or looking at partial sums to see how that behaves. But the question I'm going to ask you is, do you ask your students to do that? Do you ask your students to create visual images that represent the sum of an infinite series? Do you ask students to do it multiple ways to relate the algebraic meaning to the numerical one to the visual one? So even if it's in the textbooks, I would argue many people teaching calculus do not ask students to do those sorts of things. So why do we study infinite series? I had a meeting with one of the upper administrators at my institution, and he has a background in mathematics, and he did not think that infinite series were terribly important. He didn't think that they were useful in the real world. So why is it still a part of the curriculum? And I believe they're essential. And granted, I'm biased as a mathematician, but I think that I have some good evidence to support why it remains a significant part of our curriculum. Now, going way back, the idea that an infinite collection of positive numbers could yield a finite, putting an infinite number of numbers together, yet getting a finite number, truly was amazing to the ancients. And the fact of the matter is, infinite series intrigued some of the greatest mathematicians in history. And I want to take a look at some of the results that came about. So we see this as far back as Aristotle and Archimedes. The Grandi issue, to me, is really interesting. The alternating series, 1 minus 1 plus 1 minus 1 plus 1 minus 1. Grandi claimed that was a half, which with modern eyes looks silly from our notion as the sequence of partial sums alternating between 0 and 1 is not going to converge to 1/2. But he used a probabilistic kind of argument, saying it was 0 half the time, it was 1/2 the time, averaging that to 1/2. And that held a lot of sway for a long time. So my thought is, if some great mathematicians struggled with this concept, it certainly seems reasonable that modern students would struggle as well. Leibniz gave a more precise notion a few years later, as did Riccati. But it took Gauss, frankly, and Gauss is perceived as a modern mathematician, to finally define convergence correctly. And in mathematics education, we recognize that the historical development of mathematical concepts is often reflected in the challenges that students have. So when students try to define these notions, they use their intuition first. They look at it like Aristotle, Archimedes, and Grandi, long before they look at it like Gauss. Now, can we get students to think of it like Gauss? Mathematicians have to do that. The challenge that I think we have is how do we get students there successfully without, destroying their spirit. Take a quick look at the Oresme proof. So notice this is all the way back to 1350, proving that the harmonic series diverges. And this truly is one of my favorite proofs I've ever seen. In terms of just combining the terms, we can combine enough terms together by doubling their length each time so that we have an infinite number of 1/2s to add together. With an infinite number of 1/2s, of course, it is going to be greater than any finite number. And students also find this fascinating. So when you go ahead and you prove that the harmonic series diverges by looking at the integral, I think you should pull this out second as another reinforcement that indeed that is the case. Now, why do we use infinite series today? If you teach differential equations, you recognize that infinite series are crucial. They enable us to solve all kinds of differential equations that couldn't be solved by any other technique. Infinite series are standard in numerical analysis if you're looking at the behavior of functions. And frankly, the infinite series help us define these functions. What does e to the x really mean? I always tell my students that sine x is not necessarily opposite over hypotenuse. That is one interpretation of that concept. But the Maclaurin series of sine x, I think, really tells us the behavior of that function. And in fact, I argue that the infinite series are the DNA, right? It gives us the information that defines those most important functions. I do want to give you a warning, though. For years, I said that handheld calculators used infinite series to do computation for things like sine, cosine, e to the x, tangent, etc. That is not the case. They use more sophisticated algorithms. I included that on a previous discussion I had on infinite series, and if you have some questions on that, I'd be happy to address that later. Now, Cullinane in 2011 looked at the reasons students struggle with series. And what I tell my students is once you start Calc 2, you are moving from doing mathematics as a child to doing mathematics as an adult. You are no longer simply mimicking processes done by an instructor. Your job is to be able to identify the meaning of various concepts, prove things as you go along. So the type of problems change. We're going from more concrete problems to more abstract problems. You'll recognize that this process requires a certain amount of formality. If you ask a student to determine whether a series converges or diverges, in essence, that student is writing a proof. Cullinane says the type of reading is different. How students read these sorts of things with series is different than they're used to doing in terms of just following procedures. And how you write up one of these problems is different. So that's what was found by Cullinane. Hardy recognizes this, and I have a feeling most of us recognize this too. What students learn in the calculus class differs from what the instructor intended to teach. Rather than using concepts from calculus to solve limit problems, students tend to focus on practiced algebraic procedures used to solve typical exam questions. And if we're going to fix this, the typical exam questions have to change. So students must be asked to do more complex problems, explain their reasoning, prove these theorems, connect models from visual, numerical, graphical, algebraic perspectives. If the exam questions change, if the homework questions change, then the student expectations should change. We want to look at some of the misconceptions students have about limits and have about series and convergence of series. And you'll notice that this potential versus actual infinity notion comes up again in Rose's idea. So she's saying that the series continues endlessly, so it has no limit. Another thing we've seen, and frankly, this is one of my biggest pet peeves, is students plugging infinity into n and then evaluating algebraic. And then the other thing she says is the series gets close to the number but never actually gets there, which again, to me, seems like a reasonable idea. But if you look at the notion of actual infinity, we have a different perception in mathematics. Rowe also says the series needs to get close to a number if the differences between the consecutive terms get smaller. So these are the concept images. What students perceive is going to happen when we have a series converging. Paul McCombs, my friend, who I said helped inspire me to go down this path, in his recent research, he noticed that students do not know the prerequisite material. And if I had a yes or no question on this one, I think I'd get unanimity that students are not as strong with the prerequisites as we would like them to be. And frankly, maybe it is in our own best interest to review some of those in class, although we know that time is limited. Paul's second conclusion is something I have found as well. Students confuse the notion of what is a sequence and what is a series. Terms are used to mean the same sorts of things. And students don't know which series test to use. So if you're asking students to determine if a series converges, they have great difficulty in determining which procedure to try to use. He said the students do not know the conditions or conclusions of those tests. Again, I think I've seen that in my work. And he concludes that students struggle with notation and vocabulary, as we saw before with sequences and series. We use the sigma notation in series. And students used to study that a lot in pre-calculus. But I'm wondering, as we move to more and more standardized exams, if the high school pre-calculus program actually gets that far. Talking to some students, I seem to believe that there are certain students we see in Cal 2 who have never seen any kind of a sequence or series before. And that is obviously a challenge for us. Series do represent the transition from procedural mathematics to conceptual mathematics. Cullinane says post-calculus mathematics is often quite different in a variety of ways from the mathematics students have previously encountered. These successful students must adapt quickly and develop new perspectives on the very nature of the mathematical activities in which they will engage. And I argue that has to happen within calculus, within Cal 2. Students have to change their mindset. They have got to recognize that what mathematics is now is not necessarily what it has been before for them. So Paul McCombs and I did an early research project that we call the Concepts Inventory. And I want to show you the results that we had by looking at our students. So not necessarily easy to generalize, but worked from several sections up to quite experienced calculus instructors. So when we asked students to define sequences that was used in calculus, only 40% could define a sequence. To construct an example of a sequence, about a third of the students could construct a single example of a sequence. That's troubling. Next question, what does it mean for a sequence to converge? A little bit more than half were able to give some kind of a reasonable answer there. To define series as it is used in calculus, a little bit less than half were able to do that. Now think about this. We spend so much time with tests of convergence of series, yet fewer than half of the students were able to define what a series is. To construct an example of a series, 51% could do that. What does it mean for a series to converge? 40%. How does a series differ from a sequence? 46%. Construct an example of a series that converges to 4, about a quarter. And you could imagine which one they used. They would use the geometric series, of course. A sequence that diverges, not many could do that. A series that converges to 5, again, similar to the earlier question, we want to see if there is a difference. Numbers here were worse for whatever reason. Construct an example of a series that diverges, 66% were able to do that. And the great majority of them used the harmonic series, the sum of 1 over n. That was memorized. And then describe the conditions and conclusions of the nth term test. one of our most important ones. Only 29% could do that. So clearly there are issues that we're seeing in Calc 2. I'm looking at the chat, and I find it fascinating that sequences and series have been dropped from pre-calculus curricula. If that's going to start happening to a large degree, I think we need to rethink how we teach this in Calculus 2 to make sure that the students have some familiarity with these concepts before we throw them the much more complicated notions that come up in calculus. In our research, we identified these types of errors that were most common. As we know, students in calculus struggle with algebra. That has always happened. And I've been at this for 25 years. I don't think the students' algebra is getting better. So addressing that in Calc 2 is going to be very, very difficult for us to manage. Calculus conceptual errors happen often. Difficulties with things like L'Hopital. As Paul said, incorrect conditions are conclusions. So using a test when it's not fair to use it. Having a conclusion like the nth term convergence test that is inappropriate. Choosing the incorrect strategy. So if we're looking at a problem like this, how do we handle that? How do we determine which one is it going to be? We want to make sure students are not just looking at problems, trying to find one similar to it, and then grabbing the strategy that works. Hopefully there is some reason that they use for choosing the strategies. This next one is one that I've seen quite often, stating facts without proof. In particular with the limit comparison test. Students will say the limit is so-and-so without justifying that. So that happens often. And then misunderstanding the question or the notation. So the students get a problem, they're not sure what it means, they're not sure what the notation means. And again, looking at the comments, more and more folks getting rid of pre-calculus series, no surprise that they're struggling with the notation. So we've got some learning strategies. So, what are some things that students should do before getting ready to study Convergence series? The first thing I mentioned here is to review the algebra and calculus techniques that are necessary before studying series. So maybe it's worthwhile to give students a study guide to at least identify what the prerequisite skills are. Have the students look at those before the series unit begins. That might make this a little bit easier for us to work with. I'm saying the students need to make a serious effort to understand the notation. So what does it mean? And again, maybe a study sheet might help them be able to do that. The third one is a tricky one. Develop the notion of convergent partial sums by using technology. For several years, I have been writing little programs for the Texas Instrument graphing calculator, where the student can plug in the series to look at, and they can see what's the sum of the first 10 terms, 100 terms, 1,000 terms, whatever that is, to sort of look at those partial sums and use the technology to help us motivate that concept. And when the calculator starts having trouble adding up all of those partial sums, we can jump to a computer and use Wolfram Alpha, have it do the first 1,000,000 terms, whatever it may be. And then once they do that, I think they've got a better idea of what a partial sum is to help us get a more formal definition of a convergent series. Now, we talked about determining which test to use. Is it the direct comparison test? Is it the limit comparison test? Is it the integral test? I think it would be helpful for students to develop their own roadmap, their own list of strategies. How do you decide which tool to use in which context? And frankly, I think it would be better for the students to do that rather than for the instructor to give that to the student. To me, if the student develops his or her own roadmap, it's got a much better chance to be powerful for that individual. And the process of creating their own roadmap, to me, is a good conceptual exercise. We're going to need to ask them straight out. We want them to strive to understand the difference between a sequence and a series. And I don't think the English language helps us much, because we use sequence in mathematics one way, we use series in mathematics to mean something else. But in spoken language, you would say a series of numbers that looks a heck of a lot like a sequence. So I guess it's no surprise if these terms have sort of confused meaning in spoken language, they're going to have confused meanings in mathematics. Again, I think it's important for students to strive what it means for a series to converge. I believe that the informal notions of having an infinite number of terms that add up to stabilize at some number is what all students will start with. And I think that's fine. I think that's a good thing. The partial sums definition is very, very difficult for students to get. But if you start with the informal, intuitive notions while the students are learning the concepts, and then at the end of the unit, once you're finishing up the sequences and series, go back and formalize those topics. Formalize what it means using your partial sums definitions. Then I think students have a much better chance to hold on to them. And since this is a conceptually rich topic, students will benefit quite a bit if they collaborate. If students can work together on these problems, they can bounce ideas off of each other, they can grow through that process. Teaching strategies. So, I think this is why most of us are here. I appreciate you listening to my take on the research that shows us that students indeed do have challenges. But I'm sure most of you are here to try to get some ideas that you can use in the classroom. And I believe using technology is key. So use technology to look at the partial sums, some of the first 9 terms, 10 terms, 100 terms, 1,000 terms, and talk about the limit as n goes to infinity of s of n by looking at those partial sums in a table. Hence, create the relevant tables of data, and then convert those tables to graphs. Wolfram Alpha does a wonderful job by doing graphs of partial sums. Have students do those things as well. And then once they do this, have the students make hypotheses. They see the tables of data. They see the graphs. Have them decide, do you think this series converges or do you think it diverges? It's not a proof. Mathematicians aren't going to be happy with that. But if they make a hypothesis and then test the hypothesis, they've got a much better chance. Today in class, I hope that this is coming up in a good time in your semester, because it sure is in mine. Today in class this morning, I had the students look at the sum of 1 over n log n, which we know diverges, but very, very, very slowly. But looking at the technology for the partial sums and then going on to Wolfram Alpha to look at what happens with a billion terms was able to show them that that thing was never stabilizing, that kept growing. I think that can be very powerful for students. Here we go. Speaking of the technology, here is the sum as n goes from 1 to infinity of 1 over n on Wolfram Alpha. And it is fascinating that Wolfram Alpha feels compelled to give us a fraction. Obviously, the decimal is more useful to us, and we're seeing 5.187. Now, that is not a sequence of partial sums. That is one partial sum. But I think this is something that students should be able to see. And notice here we have the sum as n goes from 1 to 10,000, giving us a much different number, 9.7876. This also converges fairly slowly. I think with those two, the student would at least make the hypothesis that it appears as if that is not stabilizing. Here we go to 10 million. The sum as n goes from 1 to 10 million of 1 over n. Again, Wolfram Alpha gives us a number that is different from the first two that we've seen, supporting the hypothesis the student had before, but that needs to be proven with the p-series test, integral test, some sort of a comparison. So here is indeed a Wolfram Alpha graph of the partial sums of 1 over n. Again, hopefully the student would hypothesize that that is growing without stabilizing. And I mentioned tables. Here is a list of numbers for 1 over n times log n cubed, how that's behaving. And might a student hypothesize here that those numbers indeed are stabilizing, that the limit as n goes to infinity of s of n seems to exist. This is not a proof. This is helping the students make a conjecture. So I've got some other teaching strategies. I believe it is helpful to break up the unit. Most people teach the entire series, chapter, and then give an exam. And frankly, I don't think that works very well. I think it really is better to break the series unit up into 2 pieces. So what I typically do is I include the material up through the comparison tests on the exam that also includes L'Hopital, improper integrals, and such, because those topics relate well to each other. and then finish the series topics with your ratio test, root test, Taylor series, Maclaurin series, applications and such on the subsequent exam. If you do the challenging topics at the end of the series unit, the students will not have as much time to internalize those concepts. Those are important concepts. They are challenging concepts. I like the students to have sufficient time to make sense with that. Be honest. First day, tell them the series chapter is different than what it's been before, and you've got to take a different approach to studying. In some ways, it's similar to doing integrals, in that you've got to determine which strategy to use, and then it becomes a problem-solving exercise. But I argue it's even more challenging than that. As I've said before, I think you should use technology to help make a hypothesis. And I also think that the historical development is appealing to students. If they realize the greatest minds in history struggled with these concepts, it makes sense that they would have a challenge as well. Yeah, the concept image research, I think, is very good. Vinner is responsible for that. If you've never seen it, I encourage you to look at it. Vinner looks at concept images versus concept definitions. So students may be able to say what a definition is. They may be able to correctly state the definition. Yet when you ask them questions about that concept, they will respond giving very, very different things. So the image they have in their mind is essentially divorced from the definition that they say. So you need to apply opportunities to have students challenge those concept images. If they believe that if a sub n goes to 0, then the series has to converge, have them look at the harmonic series. Give them questions that will challenge those faulty concept images. I think it's important to sort of, well, this is what Colonnade says, reorganize and reframe what we're already doing. Discuss informal notions preceding the formal notions. And when I was an undergraduate, the formal notions were always first. Here is the formal definition of continuity. Here is the formal definition of limit. Here is the formal definition of a convergent series. I believe we need to take advantage of those informal notions. We need to build from the informal notions and then develop the formal notions. And frankly, that's how it worked historically. So I think we're on good ground going that way. Motivate the abstract via the concrete. Use real numbers. Show how they behave. Use technology to measure things. Link the new concepts to previous mathematical experiences. You want students to make connections. Show how this is similar to other things students have done. I believe that we need to make an effort to ask non-traditional questions. Many of them are things I've looked at before in terms of my inventory, understanding inventory of series. Things like construct 3 sequences that behave differently. How does a series relate to a sequence? If the sequence converges to 0, does that mean that the series converges? And what does it mean for a series to? And I know they're not fun to grade. Reading students' writing can be very challenging. But it makes a big difference in having them conceptualize these very important notions. Ask students to define these concepts in their own words. I do not want them to give me a textbook definition of a sequence or a series. I want them to tell me what it means to them. Be very careful with the tests, because the way this is typically done, in a 50-minute class, you may spend the entire time doing the direct comparison test. And then the students go home and do homework, and they're all on the direct comparison test. I think you need to mix those up. So while they are learning the limit comparison test, make sure there's a geometric series in there. Make sure there's a direct comparison test in there. Make sure there's an integral test in there. Mix them up. Don't have the student just be able to look at the top of the page of the homework and know which test to use. That doesn't help the student go through the process of determining which one is appropriate. I really believe that the improper integral is what should be used to motivate the notion of series. So you look at the integral from 1 to infinity of 1 over x dx and compare that to the sum of 1 over n. Show how they have to be essentially the same, either both convergent or both divergent. This, to me, I think, is the thing that ties the two ideas together fairly well. Many people have said that the order in which we do these series needs to be reevaluated. So, one question I ask is, might it be better to start with power series and Maclaurin series? Because those are the things that are actually used. If you want to motivate students that this is an important concept, if you start with that, might you get more buy-in? Might they see that this is something valuable? Rather than, starting immediately with the integral test and telescoping series. Now, I have not made that change. but it's something I'm considering. People are asking how important is the limit of partial sums concept. It is clear that students do not know it. Students never use it. As a mathematician, I really, really would like them to know it. I just think it needs to be introduced at the end of the unit rather than at the beginning. So once you've gone through and you've developed all your concepts, go back and look at telescoping series and talk about the limit of partial sums, why we can make that work. And show them those ridiculous examples, like I showed you that -1 was infinity. Because the limit of partial sums concept is terribly important for mathematicians. We want them to know that. We just don't want it to get in the way of them developing their own understanding. You know, and one thing I'd like to know is why don't we do more with series in our traditional Calc 3 classes, linear algebra classes, stats classes? I do quite a bit in differential equations. Some people don't. But if we are going to spend a significant amount of time in Calc 2, you'd like to think it's going to show up later. Certainly it shows up later in advanced mathematics, but for many of these students, they're going to see series in Calc 2 and really never see them again, or see them for one unit in differential equations. All right, so we're back to the first question here. If you've solved it, if you want to write your answer on the discussion board, on the chat, we'll take a look at it. So Susan has an answer. We'll see if Susan's right. Anybody agree with Susan? John, you know, you're a kind man, and I appreciate you putting the poll up there, but I don't want to embarrass people, so that's okay. We could just work off of the discussion board. Well, let's take a look at how I chose to solve this problem, and we can see if Susan did it the same way. And I do encourage you to give this to your students. So this is how I did it. I said b to the log n is something. Therefore, the log of b to the log of n is the log of something. And then using the log rule, the log of n times the log of b is the log of something. Raising both sides to e to the log n times log b is something. E to the log n to the log b is something. N to the log b is something. 1 over n to the negative log b is something. And then you recognize this is a p series, and then you can do the work going the rest of the way to see that for that p series, that will converge as long as b is less than 1 over e. So we give Susan a gold star for getting that answer right. Fine job on seeing that b is less than 1 over e. But I want you to think about it. If you would have given this question to your students, how would you have prepared them for it? Would you have them use technology to make a hypothesis? What is the strategy that you would use? And if you come up with other ways to do this problem, you know, feel free to send me an email. I'd be interested to see which strategies you decided to use. Well, you know, that's all I have to say for this part of the presentation before we take questions. But I will say that I have given, I think, 3 other presentations on infinite series and calculus and such, and they're all available on my Google site. The slides for this presentation are available there as well. The PowerPoint is up. So if you would like to access those files, they are available. sites.google.com/site/rwc-amatic/files. So I certainly hope that you will find those interesting. I have more problems in some of the earlier discussions. Like I said, I've given several on infinite series. I try to change them each time because I do like people to come more than once. All right. Well, I'm happy to open the floor for questions. So, John, I will turn it over to you. Questions or comments? I thank Susan again for the kind comment. I appreciate that. I am speaking at AMATIC in Nashville. I am not speaking on this topic, though. I have been asked to give a presentation on the geometry of restaurant location. I've done some consulting work for McDonald's Corp., and they asked me to help them determine where they should put locations, areas. Okay. So hopefully I'll see some of you in Nashville. Come by and say hi.
Thanks again, Bob, and if you would all like to thank Bob in the chat room, if you haven't already, that would be great, but thanks so much, Bob, for the wonderful presentation today, and thanks to all of you for participating in today's AMATIC webinar, and if you'd like to support future AMATIC webinars, please consider becoming a member of AMATIC at bit.ly/join-AMATIC.
All right. Well, thank you, John. I appreciate the time, and I look forward to seeing you in Nashville.
Oh, yes, and let me make a few more quick announcements, and then there's a survey link at the end of my slides as well. Please remember to like AMATIC on Facebook at facebook.com/AMATIC, and recordings of past AMATIC webinars can be found at bit.ly/AMATIC-webinars, and it typically takes us 1 to 2 weeks to produce and upload webinars to this archive. And please take 2 minutes to evaluate the webinar content and the presenter at bit.ly/AMATIC26. If you need an email confirmation of your participation in this webinar, please fill in the optional section at the end of the evaluation. And you can actually click on that link right on your screen right now, and it will take you to the survey. So I would appreciate the feedback, and I will pass it along to Bob as well. So thanks again, Bob, and thanks again to all of you for attending today.
Great. Thanks, John.